So okay, good evening everybody. So welcome to the second lecture of this course, Advanced Prediction Models. So I'll start with a few announcements. First of all, I don't know how many of you have seen the course website. So there's a discussion board. So mostly from my limited experience, for these types of courses, it's useful to have it's useful to make full use of the discussion board, especially with lots of questions you may have regarding the software, as in Python, using Python, or even the concepts that are discussed today. Because most of you don't have, I would say, a lot of background in machine learning, and since we are delving deep into a subset of machine learning, we'll try to cover some of these topics, but if you have doubts, please do use the discussion board. The second thing is there is a feedback form that there's a link on the website, so you can give feedback on what you didn't understand, so that we can recalibrate the course. The first assignment will be out next week. I know it's 3 weeks into the course, but since we only have 2 assignments, it's still fine in terms of timeline. And the project details will be uploaded by this weekend. So it does carry a major chunk of your grading. So so that's going to be the most work you're gonna a lot of work you're gonna spend on the project. A lot of time. So I kind of realized that this classroom doesn't have laptop charging points, so you'll have to do something beforehand. And in terms of reading material, since this course is relatively new in terms of content, as well as the sibling courses at other universities as well are relatively new. So there will be some lag in terms of providing you pre-reading material, but hopefully the slides should cover most of the core topics, and hopefully the additional reading material that I've already uploaded and I'll upload will help you further. Okay, so today we're gonna look at a couple of things that we have already seen in the last lecture, and then kind of touch a new topic. So in terms of the last lecture, we are again going to revisit the motivation for deep learning, which is 1/3 of this course, or maybe even 1/2. Then we're going to review some of the concepts that we introduced in the previous lecture, and it's kind of important to cement this basics for a particular machine learning pipeline. We looked at classification last time, so we're going to again revisit it. Then we'll have a brief segue into Python. I don't know how many of you tried the link that not just my link, but how many of you tried getting started with Python in the past 1 week? So the remaining of you already know how to use Python? No? Yes? Okay, I mean, if you know, it's well and good. If you don't know, you may be in deep trouble, since we're gonna accelerate fast. We're gonna continue looking at feed-forward neural networks, and then get to the main novel technique or the novel architecture, which is called convolutional neural network. And we're gonna look at a couple of ingredients which constitute that architecture, called convolution operation and pooling operation. Okay. So a very, very high bird's eye view of the motivation for deep learning and for business analytics, right? I mean, typically the business goal is going to be value creation, and the solution that you provide may be a product or a service, and it may have several different components to get to that solution, to the market, to the client. Typically, you may be interested in fine-tuning the delivery stack. You may be interested in how the data comes into your solution or into your product, and what are the results that go out of your solution. And then the component which this class predominantly focuses on is the third block towards the right, which is the techniques. So, 1 second. I actually have a pointer, so I can use that. Yeah, so this course predominantly focuses on the techniques part, but in reality, when you become a practitioner or a professional in any organization, techniques are the last thing to be worried about. You need to really have a critical understanding of the domain to be successful in applying your solution, and so you need to have a complete look at all the components that constitute a business analytics solution. And so before venturing into complex techniques, for example, presented in this class that you'll learn, maybe you can see if you can get away with quick and dirty hacks, maybe a shallow model, or maybe just a KNN classifier, for example, and so on. So in terms of techniques, some of these techniques I just listed out because I was going through the previous IDS 572 course, and I saw that they have touched a few techniques like decision trees, some linear classifiers, naive-Bayes classifier, SVMs, and they've also touched some exploration techniques like clustering and market basket analysis, which includes, I guess, association rules, right? What we are trying to augment in this course is to try to use some of the new generation techniques. They have been around for a long time, but have become popular now, which is neural networks and graphical models. And I'll try to justify in the next couple of slides why these have become important in today's in the current business world. So in terms of data, you can I think I alluded to it even in the last lecture. So in terms of data, you can roughly partition it into two sets. One is the structured data, and the other part is unstructured data. So structured data you typically find are essentially tables. Anything you can open up in Excel potentially is structured data. And there are examples here, but you typically have what are known as ordinal, integer, binary, or categorical fields. How many of you kind of remember from your previous course what ordinal, integer, binary, and categorical means? Do you remember what categorical means? Let's say in your Excel sheet there is a column which says true, false. It's just binary, right? You can also think of it as categorical. If there were three entries there, true, false, not available, let's say, maybe you can think of it as categorical. And among other tools, you'll see that for structured data, you can use graphical models, and especially it makes sense when there is some data missing or when there is noise in the data. Okay, when there is, for example, censored data and so on. Now, for unstructured portion of the types of data that you'll encounter, there are going to be images and very predominantly text. Most of the internet is text and images and videos. And if you're going to do any analytics on those data sets, you will either require lots of feature engineering. That's what people used to do till the turn of 2010, 2012. But the recent technique under the basket of deep learning, you can kind of alleviate the feature engineering part and focus on the deliverable, which is a forecast, a prediction that can help the ultimate business goal. Also, kind of caveat in terms of when you go into the industry is that measurable metrics of business success take priority over technical success merits. When I say that, I'm basically trying to again downplay the importance of techniques. Of course, you need to be a practitioner who has hundreds of techniques in your tool belt. Okay, you should be able to kind of do exploratory analysis. You should be able to do forecasting. You should be able to do classification, anything. But then, how does it kind of map to the business outcome? For example, a Y% increase in classification accuracy, does it lead to anything meaningful for the business or for the business unit? Does it increase sales? And if it does, then by how much? Maybe there's no impact, right? Also, for example, if you use a deep learning solution, what is the return on investment? What is the technical debt incurred, and who's going to maintain it? Do you have developers in your team who can maintain it, right? And the market reality is that for structured data, most of what industry does is kind of use simple custom coded rules because they are easy to understand, interpretable, no technical debt, and let's say one step further, you can even use linear regression linear regression or shallow models, and they are already kind of delivering very high business value, right? So that's the state of affairs today, or a couple of years ago. But that's not true when data is missing, noisy, and potentially there is censoring in the data, right? And that's when you need to kind of go for a different toolkit, a different tool in your toolbox, which is graphical models. And definitely this is not true when you have unstructured data, and that's where instead of spending lots of man hours in feature engineering, you want to try to use a deep learning technique, right? And the third kind of somewhat shallow justification is that it's a market-driven reason why we are looking at deep networks, because you need to know a set of techniques that have become popular in the industry, and then you will be able to work with both structured and unstructured data in a seamless fashion, right? So we'll go over a couple of quick business cases again to drive home the point of where where deep learning based techniques can deliver value. So let's say you're a home insurance provider and you want to check houses for risks and opportunities so as to kind of calculate the premium that the house owner is going to pay, let's say. And thing that you want to kind of change is this process where you have to manually check houses. It's not scalable, so you want to kind of change that process. And so maybe you can do something exotic, which is fly an helicopter or a drone and capture video, and then you'll have to, and now you're sitting on an unstructured data set. Now you'll have to do the things that we're going to discuss in this class. You may want to classify, if there's a pool, if there's what type of roof they have, do they have a yard, what is the greenery around the building, and so on. And there are a whole bunch of analytics that you can do if this route is followed to kind of get rid of the scalability of the previous process, right? Let's look at another example. Let's say you're an online fashion retailer, and I think this is a very generic toy example, and you want to sell clothes worn in, let's say, movies and TV shows and so on. And so, you may want to employ a couple of people who actually watch these shows, or maybe you can crowdsource. Somehow you may be able to get, what clothes are being worn or what types of clothes are being worn and so on. But again, you can actually build a certain type of video analytics pipeline where you can do, for example, detect the set of clothes, the categories, and then potentially match with merchants and try to move the manual work to a later stage. So most of the grunt work is being done by the machines. Maybe they are reaching 80% accuracy, but you're fine with that. Okay. And the last business case that I want to present is, let's say you're a sports analytics consultant, and maybe you're consulting with one of the Chicago teams. I don't know. So currently your products are crunching numbers. Okay. So you're a firm, you have some products, and you've sold it to some teams, and they're crunching numbers. So what's next? So you want to also analyze video and audio, which is the commentary, let's say, in real time. So that's the additional features that you want to add to your product portfolio. Then again, it's the same thing. You may want to kind of train an activity recognition classifier for that particular sport, train a real-time speech-to-text engine for further analysis for that limited domain, output reports that help in real-time decision making, or output offline reports, do exploratory analysis, and that helps in analyzing opponents, competitors, and so on. So these are some examples. I've focused only on the images or video type of examples, but you can find similar examples with text, right? If you want to summarize large articles, books, and so on, that may be a feature that may be added to you, for example, on your e-commerce platform. So that's the motivation for deep learning. I hope I've convinced a little bit that learning tools which can apply to unstructured data is an essential tool that you need to have, or at least be aware of. So now we're going to look at some of the things that we discussed in the first lecture. So we're going to review the previous lecture. So the reason why I'm spending some more time on the previous lecture is because it's foundational, and hopefully, if you have not understood greater than 50% of the first lecture and today's lecture, you may not fully appreciate the techniques that you're going to see in the next 10 to 12 lectures. Then we look at some details related to Python, feedforward linear networks and convolutional networks. Okay. Any questions at this point? So let's revisit the classification problem. This is one among several set of problems, but let's focus on classification for now. Let's not, increase our focus. Let's focus on one problem. So the classification problem is just kind of illustrated by this simple pipeline. You want to build this classifier, which hopefully when you have deployed it, whatever example or whatever feature vector or whatever input comes in, it's able to classify it appropriately, right? And so to design the classifier, we need 4 things. One, we need training data, right? It could be structured or unstructured. We need a model specification for the classifier, in the sense, what type of classifier are we going to build? That will capture some of the assumptions that we are making and so on. The third thing is we want to kind of objectively decide what is meant by a best model and a best classifier. That's the third point. And the fourth point is how to get to that best model. Can I do that with my training data, right? So that's optimization. Those are the 4 ingredients for a classification process. In terms of data, last time we saw that let's say we have n training examples. I'm gonna notate it by a symbol x subscript I and y subscript I, where I is going from 1 to n. So this notation is kind of clear, right? So I is just indexing the example number, and so let's say I have 100,000 examples. It's just xi is going to be some vector or some object which represents this example, and y kind of represents its label. So I haven't specified what these symbols represent, but you can, from your previous course, you can remember that it's typically going to be x is, for example, going to be a vector, right? And y is going to be a label which can be a tag, like this is a baseball, this is a cap, this is a cat, this is a house, right? It can be a string, but you can just map it to, let's say, a number. As long as you don't assign ordinal relationship, as long as you know that it's categorical, you should be fine, right? Test example, I'm just saying that I'll use this notation x subscript test and y subscript test. And as I said before, our objective is to design a classifier from these n training examples such that it can label test examples as consistently as possible with the ground truth, right? So that's data. Now let's look at models, right? We are going to kind of confine ourselves to parametric models. In the last class, I was mentioning that a k nearest neighbor classifier is a non-parametric model because it just remembers its training data, and at test time tries to figure out which training data is closest to its test data or test example, and just output like the labels of the majority around that test point. Okay, that's what it intuitively does. But we're going to look at parametric models, and in terms of notation, I was probably not very clear last time, but I used 2 symbols to represent the parameters, but I could have just said, a function has 2 parts. One is going to be just the input argument it's going to take, and the second part is going to be a parameter which specifies that function, right? I think one of you came to me and said, what about y is equal to mx plus c, right? It's the equation for a line, right? So let's say x is scalar, y is scalar. So m and c are going to be the parameters, right? X is the input. So that's as simple as it is. I'm going to use capitalized alphabet. So here I've used capital W to represent a greater than 1-dimensional tensor. So just think of tensors as n-dimensional arrays. So n-dimensional arrays are just, you can, if you really want to think about it, visualize it, just think of it as a bunch of Excel sheets. Let's say 3-dimensional array is just going to be a bunch of Excel sheets next to each other. So on the Excel sheet, you have both rows and columns, and you stack a bunch of such sheets, you'll also get some depth, right? So that's a 3-dimensional array. So in general, you can have more, but anything greater than 1-dimensional array, I'm going to represent it using a capital letter. So a matrix, right, has 2 dimensions. Row entries, so rows and columns. So that's why it's a capital symbol for a matrix as well. And for less than one dimension, less than or equal to one dimension, I'm going to use a lowercase symbol. So that's why b is lowercase. Okay. For example, even b can be a scalar. Let's say it's a parameter, but it can be a scalar, a vector. W is going to be a matrix or a tensor or three-dimensional array or four-dimensional array, whatever. The reason why we are using this particular form compared to this form is because it's contiguous to when we get to feedforward neural networks and CNNs. Okay. So here's an example. A linear model is just Wx plus b. The output of the linear model is a vector of scores. So this is also a linear function, right? Here x is scalar, m is scalar, and c is scalar. So there are two numbers which are specifying that function, right? Here w is a matrix, and I'm going to take x as a vector and b as a vector, right? So what is the so let's say I have a 10-dimensional I have 10 classes in my classification problem. Okay, then I'm going to output a score S1, S2 to S10. I don't know how many of you can see, but let's see. Is equal to some W, which is 10 cross. Let's say the input is really big. Let's say input is 96 dimensional. Doesn't matter. I mean, so this should be very clear. Sorry. X. So this is a vector because one of the dimensions is 1, right? Redundant dimension. So W is this matrix which is specifying the linear model. B is also specifying the linear model, some kind of an offset that you're providing. And these S's or output of that linear model is what I'm calling as scores. It's going to be a vector, right? I just randomly chose the dimension of the input to be 96. Let's say you have 96 hand-engineered features. For example, the columns of your Excel sheet, right? Or products of the raw columns, for example, right? Okay. Sorry, there's also a plus sign appearing, so let's not touch the screen. Okay. Okay, so what does the classifier do? So this is the model, but to complete the story, you need to kind of define what the classifier does. So the classifier predicts the class using the score vector. So once I have specified a linear model and it's outputting, let's say I fix the model. I know what W should be, I know what B should be, let's say. Then that is pretty much specifying the scores. And given the scores, I can predict the class using the score or some transformation of it in a straightforward manner. I can just take an argmax. So this is just a technical term which just you may already be familiar with. Is just the index of the maximum coordinate, right? So let's say X is actually somehow capturing the features of a image of a dog, let's say. Then hopefully, let's say one of these coordinates represents the score for whether the input is a dog or not, right? Then that score hopefully is higher than all the other scores. So when I take the argmax, I am actually picking that coordinate, and therefore I know it's a dog, right? Okay. Any questions about the data and the model?
Why are we assuming that there's only one object or one particular category it belongs to? An image can have more than one.
Yeah, an image can have more than one, whatever interesting objects in there. You can assign multiple labels as well, but we are looking at assigning a single label, right? So you can kind of you can actually capture your setting by just saying that these Y's are not just saying it's a dog, but it's a dog and a cat, dog and a table. You can kind of wrap that into the representation of the labels, right? But there are other ways to do it. So let's not go there. Yeah.
Then how will argmax work in that case? Now suppose if I want to classify dog, cat and horse.
Yeah.
So then the argmax first score would be for dog, but then how will it?
No, I'm just saying you need to read. I mean, first of all, your training data should contain. Let's say you have an image of a dog, cat, and a table in that image. Then your training data should have. Typically, typically should have. In the vanilla setting which I'm describing here, it should have training data where examples have those multiple labels, right? So your training data's YIs should not be just dog, just cat, and so on. Otherwise, you'll have to do multi-label classification, which is slightly different. I guess a variant, but we should not be concerned about that because it's a very minor change of the pipeline. So what I'm saying is your number of labels changes from 10 to the power 3. Let's say at most you can have let's say 10 choose 3 or something like that, or 10 choose 3 plus 10 choose 2 plus 10 choose 1. I don't know if you're following what I'm trying to say, but you will have a lot more score. Your output dimension is going to be a lot more if you actually think through this. Okay. Any questions? Or you got confused with my previous answer? Let me know.
So in one of the competitions that you had mentioned, so you had actually told us that you're supposed to guess out of the 1,000 categories, you're supposed to get 5 categories, and
No, you just have to guess one. So each of the ImageNet competitions, so ImageNet is the data. So the large scale visual recognition challenge, which is conducted every year, has one of the tasks as a classification task. It is actually the vanilla classification task. They show a picture of, for example, a dog, and you're just supposed to say that it's a dog. It's just that because the accuracies are bad, you are allowed to say more than a dog. You can say, oh, it probably is a dog, but it's probably also a cat, but something else as well.
In that particular task, you're allowed to give the top 4 scores.
Yeah. Instead of argmax, you're taking, you're just sorting the score vectors and just picking the top.
It will still be 10 cross 1 only.
Yes, still the same. In that particular example, it's 1,000 cross 1. You're just taking the top 5. You sort the scores, take the top 5 and show it out. Anybody not following? Yeah.
Can you give a simpler example of this?
Which situation?
This equation. I mean, I don't know what is W. Why is it 10 cross 96?
I said input is 96, right? So think of it as the columns of your Excel sheet. Let's say all your columns are some integer valued numbers, right? For example, the median house of the price, last year's house of the house. Let's say you're predicting, you're classifying whether the house is, is gonna be foreclosed or not. That's a decision variable. Let's say you only have 2 classes, right? And all the features, let's say 96 of them, are telling about the features of the house, the features of the current homeowner, what are the property taxes of that locality, and so on. So all those, let's say, are numbers. So let's say there are 96 numbers, and from those 96 numbers, let's say you can predict whether the house is going to get foreclosed or not. Okay. Then you will just have, in this version of the problem, you'll have 2 classes. Okay. Foreclosed or not foreclosed, and W will be just a 2 cross 96 dimensional matrix, right? It's basically just scoring. Okay. It's just, so the entries of the W matrix are just saying, okay, these features. With these features, the entry should be such that it scores foreclosed higher than not foreclosed if the ground truth is foreclosed, right? Is that confusing?
Is that W the weight of the feature X?
Yeah, it's basically it's a matrix vector multiplication, right? So if you just really expand it out, let's say score 1 is just let's say W1 times x1, sorry, W11 times x1 plus W12 times x2 and so on up to W196 x96. The first row of W is getting multiplied with x, and this is the output. It's just the sum of the products of each entry of W and each entry of x. Right? Each entry of the first row of W.
Plus B.
Huh?
Plus B.
Yes. That's plus B. So plus B1, right? So that's the actual score if you actually expand it out. This is just a compact notation for that.
So what does B1 represent?
It's just additional parameters. So in this, like just like C here represents intercept, right? When x is 0, how high you are on the y-axis, right? Similarly, B is just another number that you can tweak. You don't have to have a B. You don't have to have a B.
Bias that we have.
It's not the bias. We are not encoding the bias explicitly here. I mean, B is an additional parameter you may or may not want to have. It's just so you can always say my linear model is just W times X. That is also fine, but it may not work because it has less parameters than this one, which is Wx plus T. So this is I would say this is the largest linear model class that you can have, because once you add, let's say, some x square terms and so on, then it's no more a linear model, right? A smaller linear model family would be without the B. A yet smaller family would be if you restrict some entries of W to be some fixed numbers, let's say. So you are kind of restricting the family of linear models somehow. For example, if you set C to be 0, you can only deal with lines which go through the origin only. They can't be shifted up and down, right? Same thing here. If you don't put a B, you're kind of restricting the types of classifiers, types of linear models that you are searching over. That's all. Yeah. Yeah, it can be the feature vector of an image, but for structured data, it can just be all your numerical, ordinal, categorical variables somehow nicely represented, right?
So how do you get the input of a particular
Yeah. So how do you get X, which is a vector, from an image which is potentially 2-dimensional, 3-dimensional? So we'll get to that. But in last lecture we said, an image is just actually, if you think of a black and white image, it's just a matrix. Okay, each pixel is just a number from 0 to 255, let's say. So that's what it is. It's just a matrix. You can very naively, what you can do is kind of vectorize it, right? But you can kind of intuitively see that maybe just vectorizing an image of, let's say, people's faces, grayscaled, images of people's faces, it's probably not a good feature vector. You can't classify, for example, let's say the classification problem is male, female, or a child, or adult, or something like that. If you just vectorize the photos of an image which is just faces, then maybe you can't. It's not a good feature vector, but that's still a valid vectorization from an image, which is a 2-dimensional matrix. So that's kind of the core point. That previous to deep learning, you really had to figure out the transformation from an image to this feature vector, to a feature vector, which is going to be 1-dimensional. Now with deep learning, you don't really have to spend too much time figuring out these transformations of how to detect features from an image. Let's say, for example, the face of a person in an image should have, let's say, 2 eyebrows, 2 eyes located somewhat close to each other, a nose, and so on. So you would typically have detectors for all that, and then, let's say, a binary vector saying, okay, this image has a nose, this image has 2 eyes, this image has something. You could have done something like that. But we'll see that in deep learning techniques, you will kind of avoid that path. Yeah. Anything else? Okay. I think we got this. So let's look at the other two components, which are going to be now define what best model is and how to get me the best model. Those are two things. Those are left, right? So what is the best model? An objective way to define the best model is by capturing a couple of things. First thing is what is called a loss. I've represented it as L data, okay, and I've just made basically a decomposable sum, which means that it is just a sum of a bunch of numbers, and each number is just associated with the particular example in a training data, right? So I'm just saying that the loss is just the loss that you incur on the first example, loss that you incur on the second example, and so on. So what is loss? Loss is just going to capture the incompatibility between that particular example. Let's say ith example is the picture of a dog. Somehow you got features, and its true label is actually dog. But if you if your current model suggests it's a cat, then there is incompatibility, right? So the loss has to capture that incompatibility. That if you are predicting wrong, then you're penalized. If you're predicting fine, then hopefully the loss is low or 0 or something like that. Yeah, so that's what I mentioned here. And in the last lecture, we saw two examples. One is the logistic loss, Li. So now, as I said, we don't, this is just a sum of terms which are just dependent on each example, and the term for example I for logistic is going to look like this, where S1 to SP are the scores. So P, for example, let's pick 10. Okay, there are 10 classes: dog, cat, house, table, and something like that. So S1 to SP are the score. So this vector. So logistic loss for the ith example is going to be how did I score, for the true label of that image. For example, if it's a dog, what was the score I assigned to the dog compared to everything else? That's roughly what this is capturing, and the negative log is because of some other interpretation. We don't care about it. I mean, this is somehow capturing this intuition, right? So we can directly look at that. When the score is low, then this number is going to be highly, first of all, recall that this number is smaller than 1. Okay, so if you are assigning a score for the true guy, which is dog, a low number, then this number is going to be very much smaller than 1, very close to, let's say, 0. Then log of a number which is much smaller than 1 is going to be a negative number, a large number actually, because log of 0 is negative infinity, and the negative of that is going to be a very high number. That's the interpretation. Oh my god, this is dying. Okay. So the second loss is also very similar. It's just saying that what was the score assigned to all the other guys. Let's say this is for the dog. I assigned a score of 10 points for the dog coordinate, and everything else was less than 10. Let's say. Okay. Then this term is for that example. I did assign a good score to the dog coordinate. So everything else was less than 10. So this number is actually works out with 0, right? Because Sj is going to be less than Syi, and I'm assuming C positive, which I'm not shown here. Sorry. Okay. Well, then it's going to be C. Okay. Not really. So the difference is going to be negative, and I'm just giving an offset, so you can ignore the offset, the C term here. You can just ignore it for now. It's just an additional parameter, loss functions parameter. So you can see that if I give a high score to the dog, and it's actually a dog example, and everything else is low scored, then max of 0 and a negative number, I'm going to give the loss for this example of how my classifier is doing is 0. But if I have, for example, there's one other class for some other coordinate is for cat, and I gave a really high score for cat, then that particular term is going to be positive, and so I'm going to penalize, I'm going to kind of account for that incorrectness that I predicted a high score for cat, whereas the image was for dog, right? Is that clear? So these are just, and it's not like we are, designing new loss functions for every new application. These are some standard things that you can pick up from the literature. So the second component in the loss that we also went over last time was this concept of regularization. So regularization is to control something called overfitting on the training data. Okay, it's a fancy term. All it's trying to say is that I want to capture some preferences over the model I pick. So let's focus on this linear model. Here, as she pointed out, I don't really like the B term. So maybe I can penalize, a model. Among all models, I want to penalize the models which have a B term. I ideally want the B term to be 0. That would be the perfect model I want to pick, whatever be the W. But if there is a positive, if there are coordinates which are non-zero in the B term, then maybe I don't prefer that model. Okay. So you can capture that preference using this regularization business, which just means I'm going to add an extra term I'm gonna add an extra term r of w comma b, or in general r of theta. W comma b I'm just explicitly splitting because of some continuity reasons, but for the next part of the lecture. But it can be just some theta parameter, right? You can kind of club w comma b as some unknown parameter theta. So I'm going to use this notation. So for example, this is just going to be a function of the model only, model parameters only, and it's going to express preference over the models, right? The model is completely specified with w and b. So I just have to express preference over which w's I like, which w's I don't like. If I like certain w's, r hopefully is low, and if I don't like certain w's, r hopefully is high. Okay, it's just a function. It's just a maps to given a pair of w comma b, I just output a number. That number should be low for the models that I prefer. Right. So there are a couple of regularizers that we saw last time. I didn't expand it this way, but L1 regularizer is just, for example, the sum of all the absolute values of the entries of the W matrix, or it can be, if it's a function of both W and B, it can be the absolute values of the entries of the W matrix as well as the B vector, for example. Right? It's just it's an intuition here is that I don't want too many so the intuition for L1 regularization is that maybe I don't want high absolute values in my W matrix or the B vector. Okay, so it kind of encourages a lot of zero entries in the W matrix and the B vector. Intuitively, that's what it does. Okay, mathematically, it's not exactly true. So there is some additional thing we may want to investigate. With L2 regularization, it's just penalizing for large entries in the W matrix, and right now I've just written it for the W matrix, so you can always do that. Okay, I don't care about the values in B, but I care about the values in W. They should be somewhat, should not have too high values, because if any entry has a high value, I'm squaring it, so it's really exploding, and that's the penalty I'm imposing for that model, right? So I'm less preferring that model which has a high entry in one of the coordinates, ij coordinates. So when I say loss is going to be it's going to be a function of the training data, and it's going to be a function of my preference. Okay, so there is some Bayesian interpretation of all this, but we will not get into all that. For example, if you might have seen, for example, this can be just least squares. If you have seen least squares regression, this is just going to be the least squares term, and this can be L2 regularization, which encourages having weights at all the coordinates or something. We can map it or talk offline about that mapping. So this is clear. Okay. So that's what we have discussed. We have discussed the data, the model, and the specification of the loss. And this is how a block diagram looks like. So we have parameters. We have two things. One is R preference, which is captured by the regularization. Second thing is the parameters interact with my n training data, and I produce scores. From the scores, I can get the L subscript data term, and L subscript data term plus R will give me the final loss number, which is a scalar. It just tells me I have this model W comma B, I have this training data. What is, how good is that model? It's just a number that you're attaching to a model, right? And if you don't like the W comma B notation, in general, this is how it looks like. You may have a parameter. The parameter just you kind of assign a number to that parameter. And when I say a parameter, okay, I say parameters here, but theta can be multidimensional, just like the W comma B pair is one is a matrix, one is a vector.
What's the hyperbolic parameter gamma?
Yes, so I introduced that term because sorry, this is lambda, right?
Okay, lambda.
Okay, so lambda is kind of capturing how much of weight I want to put on the preference. So when you have two objectives, right? I prefer certain types of models, but the data may tell me that some other type of model is good. So this part, so for a given model, this part is kind of scoring based on the data of how good that model is, how consistent the model is with respect to the trained data's true labels, right? This part is saying, oh, there is a model which may be good with respect to the how well it kind of scores the how well the scores align with the training data's labels, but I may not have good preference for it. So you may want to balance those two objectives. Whenever you have two objectives, one way to kind of deal with both objectives is to just write a multi-objective function, which is just first function plus some constant times the second function. So, but there are other ways to deal with two objectives. I don't know if you've seen multi-objective optimization. It's a field in itself. But here, I'm just telling if lambda is very high, I'm just saying that I really want the models that I prefer. I'm willing to discount how well the models do on my training data. If the lambda is really low, I really care about how well the model is fitting my training data. You know, each li term hopefully is low, and I don't really care about my preference. Okay. So that's the hyperparameter. So basically, whenever we so in this description, we have two things that we did not set. I mean, in the sense that these are two things that we wanna set, you know, well later. But once you have quantified what is the best model, we wanna kind of optimize on this. But here, it's also not clear what to set this term, this particular parameter as. So we'll also have to optimize on that, right? So those are the three things that we may wanna optimize over to get the best model which works on the test data, right? Best classifier. So the only thing left is the optimization block. So optimization step, and the intuition is very simple. So the type of optimization that we see in this class is a very small subset of different types of optimization that a lot of people do. For example, the optimization to do scheduling logistics is very different. Optimization needed to do processor scheduling or your ride sharing scheduling or something like that is very different. Here we're going to look at continuous optimization, and within continuous optimization we're going to look at just first order methods, okay, which means that we're going to use gradients. So what is the intuition? Okay, the intuition is we're going to start with the model W0 B0. Okay, we're going to have to start somewhere so that we can search for the best model, right? We want to evaluate this L number. So for every model, I know the score that I'm assigning, right? We can evaluate that number because we have the training data. We can evaluate the L number, and then we just want to change this model W0 B0 to another pair, let's say W1 B1, such that the new L is smaller. That's the most intuitive thing you can do. And you want to repeat this. So we're going to focus only on certain types of optimization methods, as I said, first order methods, but also methods which kind of are iterative, right? I've kind of set boundaries in terms of what type of optimization algorithm or what type of optimization technique I want to use, right? And this intuition is the essence of the gradient descent methods, right? So in a nutshell, the gradient of this L score with respect to the parameters is used to change from the current candidate W0 B0 to the new candidate W1 B1. Okay, and typically W1 B1 hopefully has a lesser score. The L number is reducing. So L is like a loss, right? So we have to kind of reduce our losses incurred. So we want to kind of ensure that we kind of move to W1 B1 such that L is smaller. And so last time we looked at an example algorithm which was called batched stochastic gradient descent, where the first two terms really don't mean too much. The first two terms kind of capture that instead of working with n examples, n training data, where n could be in millions, right? In ImageNet classification problem, the problem's images were 1.4 million. The original data had 14 million images or 15 million images. The classification problem had 1.4 million images. So you can't really find L subscript data because that's a sum over 1.4 million terms, or it will take a long time to do that, let's say. So you just choose a random batch size B and think of that as my training data for this iteration, let's say, right? So that's all the first two terms mean. So let's ignore that, or it's not very crucial. Now you want to get the gradient of L with respect to parameters, the current set of parameters, let's say W0 B0 or some generic parameter W1 B. and then you want to update, which is written here, which is going to be, once you get the gradient, it somehow works out that the gradient is going to be the same dimension as the object, the parameter object. So if this is a matrix, this is also going to be a matrix, and this is a vector, this is going to be a vector. Okay, that I'm not going to demonstrate in the class, but you can verify that, and we'll see in the subsequent couple of slides how this works out. So the gradient update is just this. If I can just get this gradient with respect to the parameter, that's the notation for this. I just have to go from W0. Let's say this is Wk is 0. Then I can go from W0 to W1 by just a simple subtraction. Okay. So the missing component is the gradient, and so how do we get the gradient, right? So we looked at this core technique last time. So we're gonna test that again, which is backpropagation. So it's just a efficient way to obtain gradients. So you are just asked to get gradients, right? There are 100 different ways you can get the gradient. If you know what the computation is happening till the number L is, till you get the score L for that model, you can use calculus, sit down with the book, and figure out how to compute this object here, right? You can figure this object analytically, or even numerically. You can compute the gradient because gradient is just the perturbation of the function at close to the current value. So if you are at W0 B0, all it's asking is if I perturb my W0 B0 by a little bit on each coordinate or whatever is there, then how does the function change? L change, right? That's roughly the intuition for gradient. But we wanted to use an efficient method, and this is what is used in current, I would say, production-ready systems like TensorFlow. I don't know if you've heard of TNO, Torch, or something like that. So these are tools, software tools for running deep learning solutions. So they use backpropagation. So that's why we are looking at backpropagation. Okay. So backpropagation is very, very simple. All it's saying is that if you have a computation going from parameter w comma b so we have w, let's say w0 b0. We have some computation happening, that L data, Li, R, all that, and I got one number L. Right, that's the output. That's kind of a score of how good the model is. And I wanted to move W0 B0 to a new number W1 B1 by using gradients. Right. Now, backpropagation is all about breaking down the computation, which given these two and given the training data, which is n xi's, yi's, which are n in number, right? I is equal to 1 to n. Given this, which is fixed, from this I can go to this, and there are a bunch of computations happening, which I can represent as a computation graph. We looked at a computation graph last time. It's just, let's say for example, W11 is multiplying with x1, right? W11 is also multiplying with, x. Okay, I'm using subscript. Okay, let's fix an example. Let's say we are only taking one example. W11 is multiplying with x1, so there will be a multiplication node there. And similarly, W12 is multiplying with x subscript 2, which is the second coordinate of, let's say, the example. Then there's another multiplication node there, and so on. So you can kind of represent your whole computation of going from the model to a score for the model as a computation graph. And backpropagation was a very simple trick. It said just look locally and get a gradient from your successor node in this computation graph. Okay. Compute locally gradients of your inputs with respect to your function. For example, if it's a multiplication function with two inputs a comma b, then the gradient of, for example, the first argument with gradient of the output with respect to the first argument is going to be the second argument, right? Do you guys follow? I just said if h is a times b, then gradient of h with respect to gradient of the gradient of h with respect to a is going to be b, right? That's all I said. So you know the gradients of the function that you are computing at the node with respect to its inputs. That you can compute because these are typically going to be simple computations. Okay, addition, multiplication. Maybe there's a sigmoid or something there, but there's typically going to be simple computations. So you know the gradients of your computation with respect to your inputs. If somebody can just pass on the gradient of their computation with respect to their input, so my output is going to be an input somewhere, right? So if those guys can just pass on the gradient of their computation with respect to their input, which is my output, then I can just multiply that here, which is what I've done. This term is the same as that term, right? I can just multiply that with my local gradient to compute the gradient of g with respect to b and pass it on to people before me in my computation graph. That's the intuitive idea of backpropagation we looked at last time. Okay, so that's what happens. So you can just pass it on, then you can get the gradient of the output with respect to gradient of something which is not local with respect to inputs. And a similar thing happens when here a and b were scalars. If you instead of scalars, let's say it was a transpose b, then similar vector operations can be done. So the story doesn't change when you have vectors, okay? Except that the local gradients will now be matrices instead of scalars or things like that. And we looked at an example last time. So we had a function which had 4 scalar inputs, and the final output of the function was that 1 by 1 plus e to the power minus ax plus by, right? This thing over here. And given a current value for those parameters, let's say the current value for those inputs, a is 2, b is 1, x is 3, minus 3, and y is 4, I can compute the output, which is the g value, right? I can just forward propagate and find the output, which is the g value, 1 by 1 plus e square, okay? And then I can do the backpropagation thing I was talking about. Let's just focus on this node. This node's output was, this node's gradient with respect to itself is just 1. I know what the local computation is, 1 by 1 plus e to the power minus z, okay? This is where z is a scalar. So I know the gradient with respect to its input is going to be, is ultimately going to evaluate to this for the current value of z, which is minus 2. Okay? The gradient you can just compute, right, for functions. It's just a one-dimensional calculus. So, anybody confused here, completely lost, tell me, I can work it out, but otherwise we can move forward. So, the gradient of g with respect to its input at the current value of z, which is minus 2, is this. And then I'm going to send this value back to the plus node. And plus node's gradient with respect to its inputs is 1, 1 and 1. Okay? Because if h is a plus b, then gradient of h with respect to a is 1. And so 1 times its input, which is this number, it will be passed back. Okay? And that's what I think we did last time. So the final output gradient with respect to the plus sign's input is going to be 1 times the 1 times e square by 1 plus e square the whole square. Basically, I'm just copying this over here and multiplying it with the local gradient, which is 1. And so I got the gradient of the final output with respect to the plus sign's input, plus node's input. Same thing can be done below. It's a symmetric operation. So the local gradient is 1. So 1 times the gradient which was passed on from my successor node. And so these local gradients, dou g by dou c and dou z by dou g, these two numbers will be passed on to the previous nodes. Okay, and I'm just showing for one, because all very symmetric, I'm just showing multiplication node, we just saw what the local gradient is. So the final output gradient with respect to the input y is going to be this number. Okay. So we went through this for some time in the last class, but I just want to make you remember this because these are some of the internal things in the tools that you're using. I think in a class you need to know not just how to use the tool, but also how the tool works. So okay, so given that, yeah.
I was just wondering how much of that would come to
No, I mean, for example, if I change this from, let's say, the sigmoid function to, let's say the function here is instead of 1 by 1 plus e to the power minus z, it's z square, right? Then you should be able to backpropagate and tell me the gradient at, let's say, the current parameter values.
Okay.
At least for this small, this is a really small computational graph. You'll see that for neural networks, the number of, there's no manual thing that we're going to do for our machine learning tools. This is just to understand that how backpropagation works for really small scalar functions. So for the exam, I'm going to try to see if I can give you some sample questions during the lectures. So you'll be better prepared for the exam. Yeah. So the answer is use backpropagation to get the gradients, and then you do the gradient update. Okay. So if you actually just do this, get the gradient update, then just repeat the whole procedure of going from W0 B0 to W1 B1 to W2 B2 and so on. You'll hopefully get to some W1000 comma B1000 after, let's say, 1000 iterations, 1000 repetitions, which are going to be a really good model in terms of L data and your preference, which is captured by R, the R function. Okay, so any other questions? Okay, so now we're gonna try to do a very quick walkthrough of Python. So actually, how many of you really don't know Python at all? You really need to speak up right now. Okay, there is 6, 10, 15, 18, okay, 19, 20. 20 people. So I guess 1/3 of the class, is not familiar with Python. So we'll just quickly, go through some of the basics. Some of you may already be advanced users of Python, so ignore this, or you can correct me if I'm wrong. So it will be necessary for programming portions of the assignments. It's kind of useful that you learn Python as a part of your tool once you graduate and join industry, right? And more precisely, we're going to just use IPython, which is just an interface, a nice interface for working with Python language. So IPython is just interactive computing. So people who are familiar with MATLAB or something like that will find this very similar. Okay. So to get there, what you need to do is first of all install Python. So Python is available for all operating systems, Windows, Mac, Linux. So maybe get this distribution because it's just a double-click install. Okay. There are two versions of Python floating around. It's your choice whether you want to go with Python version 2 or Python version 3. The consequence of that choice, at least for simple programming, is there's not much consequence, but maybe later on if you want a certain particular module or package or something, some additional, roughly a plugin, they may not be written in one version or the other, right? So 2 is the older one, so it has a larger ecosystem, and 3 is a newer one, but it has been there for some years, so you can choose whatever you want. So once you double click and install Python, it will already be there in your command line. So CMD in Windows and on Linux or Mac, you can just open the terminal, and then you'll have to. So if you install the Anaconda distribution I showed in the previous slide, you're done. IPython comes by default in that distribution. But if you have installed Python in a different way, you may already be familiar with this command called pip. So you can just pip install Jupyter or IPython. So these are just synonyms, same name for the package. So these are the two things that you need to do to get Python and an interface for Python running. Okay. And then you can start up, launch a session or start working on something by typing Jupyter Notebook on your command line. What it'll do is it'll automatically open up your browser with a URL, which is a local web server URL, and will open a page like this. Okay, the page will look pretty much like this. It will have a headline, and then it will have some notebooks if there are any notebooks, or it will just be empty. And then you can start a new notebook. A notebook is just a worksheet. It's just an empty document where you enter a bunch of Python commands, and then you can click run, and they'll just run in a sequential order. Okay. We'll actually see that in a few minutes. But you can start a new notebook by going over here. There's a new phrase there, right? So you can just expand it, and you'll get an expansion like this, and you can just pick Python, whatever, 2 or 3. Okay. So once you click the new notebook, the interface is going to look like this. So I took a couple of screenshots. So the major kind of block in IPython or Jupyter, or this way of interacting with Python language, is this notion of cells. So cells are typically used to run a short bunch of statements which execute and are basically the code, right? For example, here I'm saying x is assigned the value of 1, y is assigned the value of 2, print x plus y, right? And in the second one, okay, so how do you execute? Once you write this, you basically have to press shift plus enter, or control plus enter, or command plus enter, depending on which operating system you have, and you basically run the code. So these variables, for example, so the difference between the top screenshot and the lower screenshot, it's basically there are 2 screenshots, right? With the separation somewhere over here, right, where the Jupyter Untitled follows again, is that I pressed shift plus enter, and so I got yet another code block, this cell thing, and I got the output, which is 3 here, right? But I got the output, but x and y persist. So in this cell block, I can again say print x, and x will still be there. So it's a global variable, okay? In the sense that once I printed x, although I wrote x in this code block, which is I don't know if you can see the block. The previous block is just up to this. The print command, when I said shift enter, it printed 3, and now I have got a new cell, right? In the new cell, I will still know the values of x and y. X and y are still there, okay? So that's what I mean by global variables are shared between cells, and typically you run from top to bottom, or you can also do inverse, but it's not useful. So this is what I meant by global variables are shared, right? So in one cell I said x is assigned 1, y is assigned 2, but in another cell I'm saying print y plus 10, so y is still there in another cell, right? And you just need to save your changes on this notebook, which is just a collection of cells. Okay, you should do that. Okay, so then so that's just for the setup and getting started with the notebook. We're going to look at a few quick things about basics of Python. Actually, I've posted a Python review example or Python review notebook in the course website. So if you can download that notebook and run your Jupyter space notebook or IPython space notebook, then you will see that notebook, and you can click on it, and you will be able to follow the next few slides if you want to. So now for the next 10 to 15 minutes, we're going to just focus on some key aspects of Python. I know it's very quick introduction to Python for people who have not seen it, but it will give you a flavor of hopefully the takeaway after 15 minutes or 20 minutes is that it's not a hard language at all. It's the easiest language to pick up. Okay, so what is Python? Python is just a general purpose programming language, and there are 2 versions. 3 is not backward compatible, so that's the only issue. And it's very similar to something called MATLAB for people who have had some engineering background, and it's dynamically typed. Okay, so which is somewhat inconsequential for beginners. So let's get to some data types. So when I say x is equal to 3, x is of type integer, okay, and when I say y is equal to 3.0, y is going to be of type float. So that's what I'm doing. So I'm assigning x and y to different numbers. One is an integer, one is a floating point number, and so the type is dynamically inferred, okay, and I can actually print the type of the particular variable by just writing type bracket x, and I can use different types of print commands. For Python 2, I can use print bracket the variable, or I can use print space the variable, okay. And when I do x divided by z, if x is integer and z is integer, I will get I'll get a rounding. So 3 divided by 2 is actually 1, okay. But if I divide y by z, then I get 1.5, okay. So there is some inconsistency. You know, if you are only dealing with integers, you will get integer as output, okay. Next, you have the usual. I mean, if somebody who has worked with, I guess, Java, C++, or C, you know this incrementing shortcut. Instead of x is equal to x plus 1, you can just write x plus equal to 1, right? So those types of shortcuts are available. And the double star operation is for, so the next, so y double star equal to 2 just means raise y to the power of 2, okay. So y, if you remember from previous slide, was I think 3 or 3.0, so 3.0 to the power 2 is 9.0, okay. And I incremented x by 1, I don't know, x is also 3, so 4, okay. And you can do multiple assignments, like a is assigned true, b is assigned false by just putting comma. So a, b, x, y are all variables, okay. And you can also assign a variable. For example, you can have arbitrary names pretty much. So my string is just assigned a string in single quotes, which is the ID is 676, so an error. But and then you can also print multiple variables at the same time. You can also concatenate strings by just using the plus operator, okay. And you can also, every string has multiple methods, so you can do mystring.upper to get capital letter I, capital letter D, capital letter S. So there are some small things that you can try once you open your, once you get the Python setup and then install Jupyter or IPython, okay. So these are simple things, so I don't think we should spend too much time on this one, but let's focus on the 4 basic data types, not data types, I guess, containers in Python. So there's something called a dictionary, a list, a tuple, and a set, okay. We're gonna quickly go through these 4 things because these are useful for many of the other operations that you want to do. You want to do text processing of some financial data in your in your project. You can use, for example, a dictionary or a list. If you have numerical data, you can use a list, but later on maybe you'll use NumPy, okay. So what is a list? List is just as it says, a list is just a collection of objects. So in this case, I've said my list is a collection of strings. The first string is just the letter I, second string is just the letter D, third string is just the letter S, okay. A tuple is again a collection of immutable objects. So here tuple is just a triple. It's just 5, 7, and 6, okay. And if I print them, you just see pretty much the verbatim outputs, okay. I can index the list, and one nice thing about list is that list as well as tuple is that I can index both list and tuple using this type of indexing, which is square bracket the index number. Index numbering starts from 0, okay. And list is a mutable object, as in you can replace the elements in a list. So here I have assigned C, B, and A at entries 0, 1, and 2, and I've also appended an element to the list, which is this element 5, and I have extended the list by adding one more list to the back of it, okay, which has entries 7 and 6. So if I finally print my list, I'll have 0th entry as C, first entry as B, second entry as A, third entry as 5 because I appended the list with a single element, and I extended the list with another list which had 2 elements, so 7 and 6. So this is my final list. So lists are basically, you can keep on changing them, so you should definitely handle them with care. Okay. Whereas tuples you can't change, so you have to define another tuple completely new, which is going to be a new object. Okay. Now the other two key containers are dictionaries and sets. Okay. So what is it? Okay. So what is a set? So for that, set is very simple. You guys might have seen sets in your undergrad math classes. So let's say I index the first 2 entries of my list using special indexing. Okay, so I am changing my first 2 entries of my list to a comma a. Previously it was c b a and then 576. I'm going to change the first 2 entries to a comma a. So that's what happened. Instead of c b a, it was a comma a here, right? And then when I say I want to, and this statement is just changing that list to a set. Okay. So you kind of remember the nice property about a set. It only has unique elements, right? So a string got folded into a single element in the set, or a set container. Okay. So these are all various things you can use. Of course, you don't need to use all of them. With list, you can pretty much get a lot of things done. But sets are nice, tuples are nice. If you can use them, use them. A dictionary is just what you might have already seen as something called a hash map, or if you have not seen, a dictionary is just the same as a dictionary, a physical dictionary. So you have a key and a value. So for example, in an English to English dictionary, you would have a word and its meaning, right? So that would be a key and a value. And so here I'm creating a dictionary. So course is a dictionary's name, and the key is going to be this tuple 5. I think the tuple was 576, and I'm going to assign a value which is going to be advanced prediction models 572 as data mining. And if I print the dictionary, I'll get with this key I'll get this string, and with this key I get this string. Okay. So these are some nice objects that you want to play around to get an idea of, and these are pretty much the objects with which you can do a lot of things, accomplish 80-90% of things. Maybe it's inefficient, but you'll be very comfortable with Python. Okay. And the simplest thing, naivest thing you can do, an additional thing that you might have seen in other programming languages, is a for loop. So if you have a list, then for every element in the list you can do some operations on that element, right? So for example, here for every element in my list I'm just printing it, but you can do other things. Okay. For example, here you can do for every element in my every test example in my text example list, just classify that example, right? That can be this, instead of print, it will be classify that example. Functions are also other major ingredient in any programming language. So here I am just showing the function that we use in backpropagation, which is, I'm calling it as the softmax function. Okay. Softmax takes a scalar input here. I mean, here I'm not even said what is it scalar or vector or anything like that. I'm saying return 1 by 1 plus e to the power minus z. Okay. So for example, when I say print softmax of something input which is z, it tells me z, the output is some very low number. Okay. You can check that, right? 1 by 1 plus e to the power minus z. I said z is minus 20, right? So that becomes e to the power 20, right? So denominator is huge, so hopefully this number is 0, and it's not exactly 0. You have some precision issues here. Same thing, but what I've done is, instead of passing a scalar, now I've created a list which is minus 1, 0, and 1, and I have somehow transformed it into a vector. Okay. So if I had a list and it was just numbers, I can easily transform it to a vector, and then I can pass that vector to the same function and it will do element-wise operation. So I had 3 numbers in my list. I somehow just did a simple transformation to a vector. So the vector will be the vector will have 3 coordinates, 3 cross 1. So this is the vector numpy dot as array of this will be a vector which is 3 cross 1, and softmax is going to operate coordinate wise on the vector. So for example, for the central coordinate, which is the second, the center coordinate, the softmax operation is e to the power minus z, which is 0, right? And you know e to the power 0 is 1, so 1 by 2 is 0.5 is the answer. So the vector is being printed horizontally. Okay. So you can see that for positive numbers you have kind of a, you remember this function, right? E to the power minus z as a function of z, right? This will basically go like this. This is 0.5, this is close to 1, approaching 1, and this is approaching 0. 0 and so this is what this function is, softmax function. Okay, next let's quickly get to numpy. So I'm just quickly showing you the type of things that you may want to get familiar with, right? This is not a exhaustive Python tutorial. I have put up links on the lecture 1's webpage, so please have a look at it if you haven't. So NumPy is a very interesting package, very useful package, especially for analysts, analytical work. So in the previous slide I said you can typecast a list to an array, but you can also do it this way. You can just call that function numpy.array on the list, which is -1, 0, and 1, to get an array which is A. An array, a one-dimensional array is the same as a vector. A two-dimensional array is the same as a matrix. Okay. A three-dimensional array is going to be a tensor, or four-dimensional array is also going to be a tensor, but whatever. Now the dimension is increased. Okay. So once I created this array, one-dimensional array or a vector, I can print that vector, which is -1, 0, 1. When I write the type of that object A, it says type numpy n-dimensional array. Okay, ND array. But once I type a dot shape, it tells me that the shape has basically 3 comma nothing, which means that it's a one-dimensional array, which means it's a vector. And if I type dot d type, it just means what is the data type in this array, and it says it's integers because there were no floating numbers here. And the same thing I did with a list of lists. Okay, so elements of a list can themselves be a list. So for example, this is a list of lists. So a list can have, for example, 2 lists as elements, and each element I think has is a list of three numbers, something. So if I typecast this as an array, it becomes a matrix actually, and the matrix is 1 point, 2 point, 3 point, 1 point, 2 point, 3 point, and if you look at the shape, it's actually 2 cross 3. Okay, which kind of agrees with what you wanted to do. It was a list with 2 entries, 2 lists, which themselves were which had 3 entries, and the type is going to be now float 64 because there was a 1.0 in there. Okay, and once you kind of can define arrays, you know, whether it's a vector, a matrix, or tensor, you can start indexing them, right? You may want just the first row of your matrix, you may just want the first coordinate of your vector, and so on. So that's what I'm showing here by example. So let's say C1 is, so there are 2, okay. So the indexing is just trying to capture a subset of this matrix B, which is 1, 2, 3, 1, 2, 3, right? So I'm saying, so the first coordinate is kind of saying the row number. So row index is from 0, 1, 2. Sorry, there are only 2 rows, so 0 and 1. So I'm saying just subset. Okay, what was, okay, I'll so the first statement is just saying index from 1 onwards. So row index was 0 and 1. Okay, and column indexes are also 0, 1, and 2. So I'm saying 1 onwards, and the second argument is saying 0 up to 2 but not including 2. So it's saying below this, and 0 up to 2 but not including 2. So this. So this is what is output, I think. Yeah. So if you say if I print C1, it's just 1 and 2. Okay. But if you look at the shape, it's 1, 2 dimensional. So 1 row and 2 columns. But if you do a slightly different type of indexing, then you will get actually a vector. So in one output it's actually a matrix, in the other output it's a vector. So a little bit be careful with that. Anyway, now you can also compare matrices with numbers, and you'll actually get a true-false result. For example, B was this matrix 1, 2, 3, 1, 2, 3, right? I compared it with 2, and it says first two entries are not strictly greater than 2, but the last columns entries are strictly greater than 2, so it's true. And if I can use that and as an indexing to subset as well. So in the previous slide you saw specific subsetting arguments. Here I'm just using a different type of subsetting argument. And other key thing that you need to kind of see is once we have matrices and vectors, we have to multiply them, right? So I'm defining two matrices, 1, 2 in the first row and 3, 4 in the second row. And the second matrix has 1, 1 in the first row and 1, 1 in the second row. And I'm also defining a vector which has two coordinates, 1 and 1. So if I do x star y, okay, so x is a matrix and y is a matrix, x star y is going to do element wise multiplication, right? So it's going to multiply 1 with 3, 2 with 4. Oh. Okay. Sorry, 1 with 1, 2 with 1, 3 with 1, 4 with 1. So it's the same thing. And x dot z is going to do your regular matrix vector multiplication. So we saw that in our linear models we had w times x, right? So for that you will need to do x dot z. Okay. And if you have a matrix, let's say I want to sum all its entries, then I can just do dot sum, and if I want to transpose the matrix, I can do dot transpose. Okay, dot t. One final thing, so that was very quick NumPy introduction. Since some part of this course may involve dealing with images, you may want to sometimes plot the image, as in see the image, right? In the programming language, its image is just a array, right? In fact, if it's a grayscale image, it's just going to be a matrix. If it's going to be a colorful image, then it probably has color channels. So it's not going to be just a matrix. It's going to be a collection of 3 matrices. Okay, typically it's a collection of 3 matrices. So for that, here's a small snippet of the code showing a particular image. Yeah, you just need to use the imread function from a particular package. Okay, so these packages come pre-installed when you kind of double click and install Anaconda distribution. We saw several slides ago. So SciPy and NumPy are by default installed, so you can run this notebook, which you can download from the course website. Okay. Any questions? Yeah.
What is the difference between list and tuple?
Tuple is immutable, as in you can't change it. You have to scratch it completely and create a new tuple. But a list is like a pointer, so the entries of the list, if you change, you're not scratching, you're not completely deleting or erasing everything and recreating something.
So it can have different data. I mean, can I store a character and an integer in a list?
Yeah, you can store. List is just a list of things, right? I can store 100 of things in my bag. They're all different types, right? So same thing with list. Immutable would be something you can't create, like this. Like I can't change this. I'll have to just destroy this and create another, like let's say red pen, right? So.
Could you go to the slide on NumPy, the first slide on NumPy? So A dot shape, why is it B comma? It should be 1 comma 3, right?
This one?
Yeah.
No, I mean for a one-dimensional array. I mean in this case it's a vector, so it just has 3 coordinates. So there is no comma 1 here. Okay. So that's the key thing that you need to kind of understand, why there is no 1 there.
What is that 365?
There are 3 entries in that 3 entries in that vector.
Oh, it's not rows comma columns.
No, no. I mean, you can get a rows comma columns, right? So this, look at this one. This is a rows comma column. It has one row and two columns. This doesn't have. This object is actually a matrix, which is one row and two columns. The previous object is a vector, so it only has 3 coordinates. So this distinction you will kind of understand when you play with NumPy a little bit. I guess your question is, why is this not a row vector or a column vector? That kind of stuff. Vectors are just, there is no notion of I would say, if they are vectors, there is no notion of row or column vectors, they are just vectors. But if it's a matrix, then there's clearly a notion, right? Row on an index. Okay. So we'll take a 2-3 minute break and come back.
How is the image store? I'm like amazed by this. Does it store this image like in the notebook or is it a URL pointing to that, or how does that?
It probably is storing that.
Okay.
Yeah.
Because like I'm surprised by that. Like I just downloaded the notebook and it shows up like without it having to.
Yeah, that's the usefulness of this worksheets. You can share them, and they'll still capture the results, but they will not capture the variables. So you can't. I mean, like if you rerun it, unless you have that image with you, you can't plot that image. So it doesn't store the variables. Like there are variables, like for example. There are no variables in this. Okay, image img is a variable, right? But there is no variable stored in that image. Whereas only the outputs are stored. So output is that image plot, right? So that is stored.
But if I share
here,
this
this is stored, but not x is not stored, but these output numbers are stored.
But I mean, like, if I share this notebook, then like obviously they'll have everything.
You can run. Yeah, you can run. I mean, as long as you're not referencing URLs or local.
Right. Yeah. Okay. Cool. Makes sense.
I've been reading that deep learning book, and it's great.
Okay.
I really appreciate it, so thanks for the heads up. And, I know you said we're not getting the homework until next week, but can you give me like a little snippet of like what it's going to be about, so I can just...
It's going to be backpropagation.
Backpropagation in
So we'll
Python.
see, yeah.
Okay.
So we will see already some backpropagation today, hopefully if we have time, but you probably just need to re-implement the same thing, but with a more modularized code. So in the first lecture I was talking about forward API, backward API. So you can kind of do backpropagation very naively, like an unclean code I'm going to show today.
Okay.
And you may have to clean it up. So that was probably one of the candidate questions in the exam.
Okay.
So basically you'll just deal with some small data sets and do the whole load the data, run a simple backprop to do gradient descent, and just look at tested codes. We're actually going to run through one example today.
Okay, cool, thanks.
Is this one you want us to use?
This is Spider, yeah, but I said IPython, right? So did you install Anaconda Python?
I think so.
Okay, this is the same thing, except you can't use this extension IPYNB in this representation.
That's why it looks weird.
Yeah.
So I can't use it.
So this is IPython, right? But you'll have to run IPython in the command line. So I don't know where command line comes in this.
But if I use the command line,
Yeah.
so I actually do install Python. I don't know if this is what it means.
No. Yeah.
But I can install pandas.
No, if you
or
do
something.
No, if you do CMD, then you get something, right?
You mean this?
Yeah. Then if you do IPython notebook, Okay, Jupyter Notebook. It will open up your browser.
So I should use this one for your assignment. I don't know, like so many things.
No, it's just to see the thing that you opened there, right? So you can just go to that directory wherever you downloaded that .ipynb. So did you download it in downloads or desktop? Or you can just it's just a file browser, right? Just go to
I
wherever.
did download this.
No, that not that the .nb file that you were trying to open in Spider, right? In this one,
This one.
where was that Spider thing?
Here.
Okay, yeah. So where is this file?
Where is this? file?
Downloads, right? Just go to downloads in that browser.
Go to my
Browser is where is the browser? I don't know where the browser. Okay, yeah.
Okay,
that's
the
fine.
browser.
Yeah, just go to downloads,
Downloads.
and if you click any one of them, so just click on the file itself. No, just the file itself.
File itself.
Yeah. It should open. Oh, you installed 3. Okay, I mean, if you just want to see the, I mean, you just have to copy paste this into another new notebook. So you have to create file, new notebook, and do the same thing. You can't run it here, but you can see what the screenshots that I showed of what you can do is listed here.
Okay,
So you can, if you open the file there, it looks very bad. But if you open it here, you'll see, and you'll have to retype it. Not retype it, but copy paste it into a new notebook.
Okay, so I don't understand this part. Like, how do this goes up to here?
It's just indexing, right? I just told you if you have a huge matrix,
Yeah.
the 1 colon and 0 to 2 colon is just saying 1 colon means anything below, anything after 1, and 0 to 2 means 0 to 2 excluding 2. So this part is output, which is the 1 comma 2 outside, right?
So under
The first print
one-
statement is showing the first print statement. 1 comma 2 is being output, right? That's because it's printing the first row and the first column and the second column of the B matrix. That's what I want to print. C is just the first row. Sorry.
The C2.
Yes.
C goes up like this.
C2 is again the same thing. It's saying pick the first, pick row number 1, and again print 0 to 2. But it's just that it's printing the same thing, but it's a vector. So there's a difference. This is the matrix because it has 2 dimensions. This is the vector. So if we index it this way, it becomes a vector. If we index it this way, it becomes a matrix. That's what I wanted to show. But if you go through so I've put the links. So you should just go through the tutorials. The material, yeah. So you will understand. Okay, actually, any pressing question? Yeah, tell me.
Now, Professor, I have just wondered, when you say the regularization, is it with respect to each of the entry in the W?
It's a function of the parameter. So it can be every entry. It could be something else, right? If you have a matrix, whatever functions you can create from a matrix. Like you can pick the singular value, a bunch of singular values if you want to. But if the version I showed you is just picking every entry and taking the absolute value or the square root entry and summing them up.
So the regularization term is not for a whole function. You mean to say it's for each entry?
No, it's a function of the matrix, right?
Yeah, it's a function of
And
matrix and the vector.
By general, it's a function of matrix in the vector. A function can be just pick the first coordinate of the matrix. That's a function.
Also, the regularization term can refer to giving the first one.
No, the example I've shown you, they take every entry, take the absolute value, sum them up, and that's the R function. So input a matrix, take every entry, take the absolute value, sum them up, output them. That's the function. That's the R function. L1 function I showed you. That's the R function. But you can choose any arbitrary function.
So, when you say a loss function, does that also apply for each and every entry?
No, loss function is for a given W. It's for all the entries of the parameter take part, but loss function is kind of parameterized by the examples. So Li, Lj, L1, L2, L3, they all sum up to give L of the data, but each one is dependent on each example in addition to the parameters. Regularization is just a function of the matrix or B,
But how
whereas
does it penalize
what penalizes? So R penalizes the model because it's functional model. L penalizes data, not fitting. It penalizes the model by saying you gave me a model, but it's not predicting the right score or the right label, right? Because in training data you have both X and Y. If you gave me a model, I can tell you that the model actually said Y or not. So yeah, Li does characterize whether the model is good or not. If the model is bad, L will be very high. If the model is good, L will be close to 0.
and regularization terms?
It's just focusing on W matrix only. I prefer diagonal matrices. I prefer tri-diagonal matrices. I prefer zero matrix. Let's say things like that.
Can you share some reading material on that, like just so that we can be clear, like about the regularization and the loss?
Yeah, sure. I actually have something about machine learning in the lecture 2. You should read that paper. It's 6-7 pages. That will give you a little bit more intuition, but I'll add the regularization material.
And I just found out, like when we have Wx plus b,
Yeah.
so why can't this be the bias? Because whenever we have a linear regression model,
This
say,
is the bias. Yeah.
this is the bias.
Yeah. I have used bias multiple times. You'll see. Okay. So let's get back to the course. Actually, I think we only have 50 minutes, right? So what I'm going to do is skip a few slides because the slides are about running the linear classifier in Python. So actually, if you go to the course website, I have given a couple of IPython notebooks, right? So they implement a linear classifier and a 2-layer neural network. Okay. Let's, instead of going, so I was planning to go through the code of these linear classifier and the neural network. They are implemented according to what we have discussed so far. So we have to specify the data, the model, the loss function, and do the optimization using backpropagation. So those 4 things have been done for a linear model and for a 2-layer neural network. We are not going to go through the code, okay? So actually, we are not going to go through the code. We will just look at the results of the linear classifier and the 2-layer neural network. And this is very toy data, so this doesn't scale to the high dimensional data sets that you will actually work with. Anything greater than, let's say, 2 is actually high dimensional because you really have to, anything greater than 3, for example, you really have to like project it into lower dimension. Let's say if you had 4-dimensional data, 4 columns in your Excel spreadsheet, then you really can't visualize the 4 coordinates at the same time. You really have to pick 3 coordinates and look at it, in terms of spatially how does the data look like, or pick 2 coordinates and look at a scatter plot, right? So for these scripts, the data is actually just 2-dimensional. So the data looks like this. Okay. So there are 3 classes: the blue class, the red class, and the yellow class. And so each data, okay, is captured by 2 coordinates. Okay. So the x vector is just 2-dimensional vector. Okay. So it's 2 cross 1. Right. Let's say if you pick this point, right, the class of that, or the label of that data point, where is that, is blue, and its first coordinate is minus 0.7 and the second coordinate is let's say 0.9, right? So that is the data that's given to you. Minus 0.7, 0.9, blue, right? That's the data. And similarly, data is there for all these other points. I think there are about 300 points here. So 100 per class. It's synthetically generated. Okay. And so if you look at the IPython notebook I've shared, it talks about the data a little bit. It talks about the W and B parameter, for example, here, right? And some value of the hyperparameter as well, the lambda that you saw, and define the total loss function. So if you look at the notebook, then it will have the data, the model, and then we perform batch SGD using Backprop. But the batch is just, I don't care about batches. I'll pick the whole training data, which is 300 points. 300, n is 300 here. And I'll train it using backpropagation. Okay. So the backpropagation code is just a for loop. So I said repeat, right? So repeat 200 times. Move from W0 B0 to W1 B1 to W2 B2 and so on. This is a little bit vectorized code, but you can actually kind of map what's written here to, for example, this is x scores is e to the power SYI divided by sum over e to the power SJ or something like that. So we saw logistic loss, right? So that's being computed here, and then the rest of the gradients are being computed here, and then the gradient update is just W is equal to W minus step size times my gradient. That's what's happening here in code. I highly recommend that you spend a lot of time trying to figure this out because it is using a lot of tricks, vectorization and so on. It will be very helpful, and you can definitely reach out to TA or me in the office hours to understand what's happening. Okay. Once you kind of do that backpropagation and get to some W subscript 200, comma B subscript 200, that hopefully is a good model according to the loss function you've chosen, and you can kind of after you've run that for loop for 200 times, you can see how it does on some other set of data. Here I've just kind of used the same data as training, which is a bad idea, but you can test how the classifier is performing according to, so you see the classifier is picking the scores and taking the argmax as in the coordinate of the highest score, and is just seeing whether the predicted class, which is a number from, let's say 0, 1, 2, in this case there are 3 classes, 0, 1, 2, is the same as what's there in the ground truth. Okay, so ultimately you'll see that the classifier looks like this, as in what have I done here. The original data is just plotted as is, and I'm plotting what are called decision boundaries. Okay, what are decision boundaries? So there are 3 classes here. So in some region of the feature space, so this is just 2-dimensional data, right? So in some parts I should be able to say this is blue, in some parts I should be able to say it's red, in some parts I should be able to say it's yellow, right? But with linear classifier, I chose the linear classifier model. Okay, and so the decision boundary just says in this region the score for the red class is higher than the score for the blue class and the yellow class. So it's basically splitting up my full feature space, which is just a plane here, into parts where the score for one class is higher than the score for the other classes. And you'll see that the score for the red class is higher than all the other 2 classes in this region, so that's why that's colored red. Okay. Ideally, what you want is the red region should kind of follow the red cluster of points right here, but it's not doing that. Okay, that's probably because not just probably, that's because the classifier is limited. It's just a linear model. It's just a linear model. Okay. Any questions at this point? Yeah.
If you have the value of W, how do you get this operation?
Yeah, so this is a very, since it's a low-dimensional, 2-dimensional example, I can kind of grid every point. As in, let's say I take a grid from minus 1.7 to plus 1.7, let's say whatever this is, and minus 1.7 to 1.7 there, and create a grid, as in, I'll define this point, define this point, define this point, define this point, right? For every pair of points, I'll classify it and see what's the highest score. Whichever coordinate is the highest score, let's say blue is the second coordinate, if that is the highest score, I'll color that point blue, and I've just created a contiguous version of that, right? If all these were blues, then I would just, I just made it, smoothened it out. That's what's happening here. That's just for illustration purposes. I mean, real life data sets will not be like this. It's just to get an intuition about, even in low dimensions, linear models are not doing well, right? So let's get to, we are still on review, which is not great. But okay, so feed-forward neural networks were also introduced in the last lecture. So let's focus on a two-layer network. It's called two-layer because you can see two gaps, right? There will be some weights or parameters on this side. There will be some weights or parameters on this side. Okay. It's called feed-forward because all the arrows are in one direction. Okay. They're all going from left to right. And typically feed-forward neural network also implies what is called full connectivity, which means every blob or every circle is connected to every other circle to the left of it, in a sense. So these circles form an input layer, these circles form a hidden layer, and these circles form an output layer. Okay. So I'm trying to kind of give you a notion of terminology as well. So in a two-layer network, there is going to be one input, one hidden, and one output. Let's say it was a three-layer neural network. Then what would change? Yeah, there will be two hidden layers. Input and output will be the same. The number of output blobs or circles there is just a number of classes. So in a running example, there should be 10 blobs there. Okay. The blob, I guess, is a node, and the node is gonna perform. Will also have something called a nonlinearity. Okay. So for example, the node can be 1 by 1 plus e to the power minus z of its input, if its input was scalar. But you can see that the input of, let's say, this node is three arrows are directing to it, right? Just think of these three arrows as the three coordinates of the input, like x1, x2, x3. Then what's happening is that node is computing W11 times x1 plus W12 times x2 plus W13 times x3. 1 second. Yeah. So this is what's happening. So the edges kind of represent. You can tack on a weight to the edge, right? So the three weights, which are going to be the parameters. The input, let's say for example I is going to be a vector, right? In this case, the input is three-dimensional in this picture because there are three nodes, right? There are three x1, x2, x3 for each example I. So let's fix an example I. Okay, ith example. Let's say it's first example or whatever. Once you fix the example, there are going to be three coordinates for it. Each of the three coordinate numbers are being passed on to the hidden layer. Are being passed on the hidden layer first neuron. Okay, this is called a neuron. And when they are passed on, that neuron will locally do some computation. That computation, one computation it definitely does is going to be weights times coordinates, right? That much it will definitely do. But what nonlinearity it uses, it could do 1 by 1 plus e to the power minus of this sum. Okay, let's call it sum. Or it could do max of 0 comma sum. The sum is the same thing. Okay, over there. We kind of saw this towards the end of last class. When it does, so this is called a ReLU nonlinearity, and this is called a sigmoid nonlinearity. So we have seen the sigmoid curve towards the end of last class. So if you really want to write it as a model, like you don't really care about this graphical representation, it's too confusing. Why are there arrows going here and there? You can, in fact, this model, this is the functional representation of a two-layer feed-forward neural network. Okay, where x is still that vector that was there in the linear model. W and B are parameters which are between the input and the hidden layer. Okay, basically you can just tack on to the hidden layer. And W2, B2 are parameters between the hidden and the output layer. Okay, but if you forget about the graphical representation, this is the model that we are considering. Okay, this model is not linear because this max operation is not linear. Max of 0 comma any number is going to be a very non-linear thing. It's going to be 0 when the input is 0, when z is less than, so let's say x-axis is z, so max of 0 comma z is going to be less than 0 is 0, and if it's z is positive, then it's going to just pass on z. That's why it's called a non-linearity. If it was a linear function, then for a scalar it's just alpha times z, where alpha is any non-zero constant, right? That would be a linear function. It's a non-linear function. And that's why. So this non-linearity will be inside the hidden node or hidden blob circle over there. As in, it will parameterize that hidden node, and so yeah. And the output of the nonlinearity is called an activation. Okay, it's just a definition. It's just a jargon being used. It just says that okay, if input was somehow, because this, remember the z is just weights times x's, right? Because I'm doing w times x here, right? Just focus on the first row, and x is anyway a vector. Just focus on the first row. Okay. So w times x is being multiplied, and I'm adding just the first coordinate of b, right? So I'm getting some score roughly. It's not really a score. I'm getting something that's being passed through a nonlinearity at the first hidden node, the center circular blob at the top. If it's less than 0, I'm just passing out 0. If it's greater than 0, I'm passing out z. So that's the full computation happening at the top node. And the output, whatever I passed out, passed to the next set of nodes or whatever, is called the activation. Okay. Is that clear? So we saw this table, but ignore most of the entries. First entry you should be familiar with because we have kind of used it a couple of times in the past lectures. It's just a sigmoid, goes from 0 to 1, kind of squashes your input. Scalar input is between minus infinity to infinity. It compresses them to a number on the output which is between 0 to 1. Okay, the sigmoid function here. Tan h also does something similar, but it kind of squashes between 1 and minus 1. Okay, you can kind of investigate that by setting very high values as inputs, like x is 100, just see what happens, and x is minus 100, just see what happens. You can kind of see that how the curve looks like. And ReLU is the max of x and 0, or max of 0, x that we were talking about. So that's the nonlinearity. These are types of nonlinearities that you could use. There are lots of design choices, but let's just stick with what is popular. So let's stick with ReLU. Okay. I think we discussed what sigmoid has in terms of issue. In terms of, let's say, if you are doing backprop with sigmoid function being sitting on top of a node, then whatever gradient you're getting, you can multiply the gradient with the sigmoid's output's gradient with respect to its input, right? And that you can actually numerically, actually analytically compute. Okay. So ReLU is what is kind of superseded the previous nonlinearities in terms of performance. Just model types. Models which have ReLUs as nonlinearities are slightly better, not slightly, but they are performing better in terms of prediction, classification problem, compared to models which have sigmoids as nonlinearities. That's all. That's the difference. So again, it's a max of 0, z. So what happens is, if the input is less than 0, then gradient is not passed, but if input is positive, gradient is passed. So that's a property you can again see, and we discussed it last time. Okay. If I have time, I'll get back to this again in case it's not clear. But we want to repeat the exercise, yes?
So to evaluate the model, we have to try different nonlinearities every day.
You could if you were living in a silo, but a lot of people have tried out all these types of nonlinearities, right? 1986 to 2017 is a long time. A lot of people have tried all these nonlinearities, and the ones which are more recent are somehow trying to overcome the deficiencies of the previous ones. If you don't care, like by default you can just use ReLU, which came up in 2010. But if you really want to eke out X% where 2%, 3% more improvement, you may try these other ones. But again, you have to tie it back to the business goal, whether 2% improvement in image recognition or something can actually lead to valuable output in terms of sales or LTV or something like that. Okay, we looked at ReLUs. So I have also, I think, given a feedforward neural network example in the course website. So it's exactly the same as the linear classifier example code. It takes the same data, except it has more parameters. So if you look at the linear classifier's parameters, it had just W and B, right? W and B completely specify a linear model, but feedforward neural network will have a couple of additional parameters. First of all, a second pair of W and Bs, because there are two kind of edges in that graphical representation. It will also have a choice of how many nodes do you want to have in the hidden layer, because you can have 100, 1000, 1, 2, you can change that. I've just picked, I think, 100 here, and that's it. And then your for loop will change in terms of course, your computation of the loss is the same as you are doing in the linear classifier, but the backprop steps will be different, because in a two-layer network you have to be more careful of how you do the backprop. If you can, of course, see the computational graph, it's quite symmetric. So if you can work out for because there are only three computation nodes there. In fact, not three, just two computation nodes. So you can do simple backprop. So once you get the gradients, you do the gradient update, which is the last part here. Now W is equal to W minus alpha times gradient of W, gradient of the loss with respect to W. Okay, that's what's happening here. And if you run this in a for loop for a long time, you can get some, you can assess the accuracy, as in did my model, which is this two-layer feedforward neural network, did do well on, let's say, some test data. Here I've just proxied test data has to be the same as training data, but you can see how it does, and pictorially you can see how it did, right? Here, because of the nonlinearities, it's able to kind of get nonlinear decision boundaries, and you may even say that it has overfit potentially. But so this is considered, I guess, a better classifier than the linear classifier you saw. Okay. Any questions? So you can anyway, you have these two Python scripts, Python notebooks. You will have to use IPython. You can't just open it in text file because it will not look nice. If you open them, you can run them locally on your machine. There's also the data, I think, small files that you have to put in the same directory and run it. If you're facing troubles, do contact the TA or myself during the office hours. Or actually, you can use the discussion board. It's a good opportunity. So let's get to the core concept of today, which is a convolutional neural network. Okay. So I'll kind of display a slide that I'd shown in the first lecture towards the beginning, which is this image classification task. So this is actually a success for convolutional neural network. So if you remember, this ImageNet large scale visual recognition challenge has a classification task. The original data has 22,000 categories across 14 million images, but this classification task is somewhat, one order of magnitude smaller. It has 1,000 categories and 1.5 million images, and you are allowed to, once you get the score vector, you can tell the top 5 score coordinates, and hopefully one of them is the right one. Okay, and you can see the error has been decreasing quite a bit over the past few years, and the jump from 2011 to 2012 was, in absolute numbers, 10% improvement. Was attributed to deep architecture. Okay. So CNNs are not very complicated objects. It's actually very similar to feedforward neural networks. In fact, it's pretty much the same in terms of what computation is done. It's just the way the edges are arranged that kind of slightly modifies, right? So each neuron or node is associated with weights and a bias. So if you recall the the additional nodes don't matter. Let's say. If you recall the feedforward neural network that I had pictorially represented a couple of slides ago. Let's say input was 3-dimensional, then there would be 3 edges like this, okay, and from the hidden node or a neuron, that's what it's called, there would be 2 edges to the output layer. Okay. Because there are 3 edges and because there are 2 edges, and 2 is the same as the number of nodes or neurons here, and 2 is the number of nodes here. Sorry, 3 is the number of nodes here. This is called fully connected network. Okay. So what's happening in this? So when I draw these graphically, what is happening is this is capturing x, first coordinate of x. This is capturing the second coordinate of x. This is capturing the third coordinate of x. These 3 numbers are being passed to this node. This node locally has W11, W12, W13, and D1. Okay. I had a matrix, right? So there were other hidden nodes. So let's forget about them. In the W matrix, I'm only interested in the first row, which is W11, W12, W13, and the B1. Out of the, let's say, there will be 4 such rows because there are 4 hidden nodes. What is happening is that I was just multiplying x1 with W11, x2 with W12, x3 with W13, and summing them up, and then some nonlinearity was being applied, right? That's pretty much what's happening, and that nonlinearity, after the application of nonlinearity, whatever is the output, that's called the activation, is being fed to the next layer. Whether it's a hidden layer, whether it's an output layer, depends on the architecture. Now, in a CNN, it's the same thing. Each neuron is associated with a bunch of weights and bars. It's the same as feedforward neural network. And what happens in a feedforward neural network? Node receives an input, performs dot product of vectors. So this is a vector. The x is actually a vector, right? x11, x1, x2, x3. This is a vector. This is a vector. You do a dot product, apply the nonlinearity. Actually, probably you want to add the bias. This plus this plus this is a scalar. Apply the nonlinearity. For example, max of 0, z. And that's the output, spit it out, right? The key difference between a fully connected network and a convolutional neural network is going to be the number of parameters. So these are the parameters, right? W1, W11, W12, W13, D1. These are all the parameters of a feedforward neural network. I'm going to somehow reduce the number of parameters and still have a network, and that's going to be a CNN network. So the whole intuition that you want to derive is, how am I going to reduce the number of parameters? Doesn't make sense right now. But we will see how the parameters are reduced. And why should I care about reducing the parameters? Because I will try to capitalize on something about my domain, my context. My context is going to be images, as in vision problem. In the vision problem, I'm going to exploit some properties about the input data, which is that precisely that they're images, and try to use some intuition from there to kind of shrink the number of parameters I have. Maybe here I have, let's say this is a 4 cross 3 matrix, let's say 4 hidden nodes, right? So 4 times 3, 12 numbers, 12 parameters are there, and then here 3 parameters are there. So instead of that, maybe I can get away with, instead of 12, maybe I can get away with 6. You know, that's going to be the objective of using a different architecture, and I can do that because of the domain. Okay. So again, pictorially, what's happening in feedforward network, given a vector xi, given a vector xi, the whole network, it's going to transform it into a score vector, right? Ultimately, the whole operation is about going from a feature vector, which is some dimensional, in this case 3-dimensional, to a score vector, which is whatever the number of classes are, right? And you pass through a sequence of hidden layers. You can have just one hidden layer, you can have more. And each neuron is fully connected to the previous layer. That's what I was mentioning, that if this was a hidden layer and this was also a hidden layer, then this neuron would be connected to every node in the previous layer. That's all. That's a characteristic of the feedforward network. Okay. Any questions about feedforward network? I think this was a picture from before. Okay. Now let's look at a particular data set, which is the CIFAR 10 data set. So as the name implies, it has 10 classes, so 10 labels. Okay. And each image is actually a colored image. Okay. It's not a black and white image, so it's not a matrix. Since it's a colored image, and image sizes are quite small. It's just 32 pixels by 32 pixels by 3 for 3 color channels. So you can just think of it as 3 matrices stacked next to each other. If you did not look at it as an image, right? It would just be 3 matrices next to each other. Okay, just numbers. Each matrix would have a number between 0 to 255, and that's how you would look at it. But the nice thing is you can actually plot it and actually see it as representing an image. Okay, like a machine will just see 3 matrices with numbers in them, and that's it. That's going to constitute an image.
What does each matrix represent?
Color intensities of RGB, yeah. I mean, yeah, in this case, yeah, but you can have other things like different colors, and not just RGB, you could have some other color, right? Yeah, here it's just RGB intensity values. So what would be X here, right? I have a 32 cross 3 dimensional array, right? It's going to be a tensor. It's not a matrix. It's a sequence. It's 3 matrices. If you think of a feedforward network, if I vectorize that, right, I can vectorize the whole image. You know, conceptually, I can think of it as a vector, right? Then it's going to be 32 times 3 coordinates of the x, right? If I just vectorize the first matrix, as in append the second row as an extension, append the third row as another extension, and so on. Do you know what is meant by vectorization? Do you guys know what is meant by vectorization? Everybody knows? Who doesn't know? Okay. A vectorization of a matrix is very simple. If, let's say A, B, C, and D are entries of the matrix, then the vector, so vec operation on this matrix, let's say M is the matrix. Vec of M is just A, B, C, D. That's all. It's just stretching it out completely, right? And if it's a tensor, just do for each matrix. Let's say here there are 3 matrices. Do this same thing and then append it below it, right? That's all. It's just making a 1-dimensional vector out of a 3-dimensional array. Okay. If you vectorize the CIFAR 10 example, each example is 32 cross 32 cross 3. You would have so many weights, right? 32 times 3 weights interacting with the vectorized version of the input, which is a 3-dimensional array, right? Which is not that big, but if your image was 1280 times 800 times 3, then you are in trouble, right? Just one neuron's weights are 1,000,000 in number, right? That doesn't, 1,000,000 numbers for this guy, 1,000,000 numbers for another node, and so on, is just unmanageable. Okay, because the number of hidden units in your number of hidden layers is also variable. You may not want to have just one hidden layer, and in each hidden layer you may want to have multiple neurons. So each neuron cannot be associated with so many parameter coordinates, right? So that kind of motivates, a parameter reduction, right? And so we'll try to reduce parameters. So let's ignore these neuron point of view, and let's look at it from a block or a system point of view. We'll look at it from layers point of view. Okay, so when we'll discuss CNNs. So the idea is that layers will have width and depth. So if you look at a feedforward neural network, okay, actually I have a picture, so I'll show that. So the new idea is that there will be, so if you look at feedforward neural network, this was just a bunch of nodes in a linear fashion, right? There was really nothing happening here. A hidden layer would have, let's say, 100 neurons, then each neuron was stacked below each other in the graphical representation, right? But we will see that we will have, so that would be considered a layer, but we'll see in CNN that we'll have a layer which will not just have something like a height, but it will also have a width and a depth. So it will be like a block. And the depth would be of that of a layer and not the depth of the network. But that's just a point to not get confused about. So what do I mean? I mean, this is what I mean. So here I'm plotting a different feedforward neural network. It's a two hidden layer feedforward neural network. input has these dimensions 32 times 32 times 3, right? And the final output is I mean, here it's only being shown as one node, but the output layer, which is in this light green color, is supposed to have 10 nodes, right? Because there are 10 classes, because I need 10 scores, right? Now instead of that, we'll have a layered representation. Okay, we'll get into what is there in each layer, but a layer will now not be just a collection of hidden neurons with just one dimension, which is the, let's say, height. Okay, a layer will have both depth and width. Okay, and so what does a layer do? So each layer in the feedforward neural network was getting a bunch of inputs and outputting some bunch of outputs, right? The inputs were at any layer, the outputs were going to be a vector, and the inputs were also going to be a vector. Okay, for example, the input layer is a vectorized form of the image. The output of the hidden layer, first hidden layer, is also going to be a vector of activations. Right? That's true for feedforward networks. Now, for CNNs, input is going to be a three-dimensional array. So you need to visualize that. Okay, I'm not going to vectorize my image. My image was anyway a three-dimensional array, right? I'm going to do some operations in the layer, which will be clear later on. But the output is also going to be a three-dimensional array. I've disbanded the idea of vectors now. I don't want to deal with vectors. I want to deal with three-dimensional arrays. And if you think of it this way, I go from a 32 cross 32 cross 3 three-dimensional array to a 1 cross 1 cross 10 three-dimensional array. So some transformations are happening in layers such that the layers outputs are also tensors, as in 3D volumes, such that at the end of the whole operation, I'll still get a 3D, canonical 3D volume, which is just 1 cross 1 cross 10, where 10 is the classes. Instead of just thinking of it as a vector, I can think of it as a tensor, where each row is just one row, column is just one column, and the third dimension has scores, right? So for CNNs, the conceptual view, again I'm repeating, is that we're going to think of input as a three-dimensional array. The intermediate outputs of my layers are still going to be three-dimensional arrays. Okay, we'll now discuss what the layers are. Okay, so there are three types of layers, which we will now go into the details of. Once you understand the layer view, then only we can get to the internals of the layer. So you should be not confused about the layer point of view for the convolutional neural networks. Okay. So now I'm going to describe. So there's going to be three types of layers in a CNN. One you already know, which is the fully connected layer. So in that case, you pretty much may think of it as a fully connected, the hidden layer of a fully connected, feedforward neural network, because that's what it is. So every node is connected to every other node, either on the input side or on the output side. Okay. So in this case, I'm just writing it as the output of that layer is 1 times the number of nodes in that layer. So it's a very degenerate output, so which you already have seen, right? And the two other interesting layers are going to be convolution layer, from which you get the name convolutional neural network, and a pooling layer. Okay, pooling just means kind of downsampling, as in if I have two numbers, I pool, means I'll just take an average or take a max or min of the two numbers, let's say. That's what pooling means. Convolution, actually you don't need to know what convolution is. When we say convolution, at least in this context, it's just matrix multiplication. Okay. What operations go on in this layer and how are the neurons arranged in this layer are the next questions that we're going to ask. So let's say our classification data set is the CIFAR 10 data set. So we know we have 10 classes and we know the input dimension. Let the architecture be as follows. I'm just describing the layers. I'll have an input layer which is 32 cross 32 cross 3. I'm going to use a convolution layer, which we'll get into. Then I'm going to use a pooling layer, which we will again describe later. And then we'll get a fully connected layer, which we know is just 1 cross 1 cross a number of neurons, right? And once the output of the fully connected layer is just going to be, let's say, 1 cross 1 cross 10. So because there are 10 classes. So we have seen a full pipeline of a CNN, which goes from images to a score 3-dimensional array, which is 1 cross 1 cross 10. But now we're going to look at what the convolution layer does and what the pooling layer does. Okay. So actually, there's a lot of similarity. So convolution layer is a big block. Okay, is an important conceptual block. But some of the things that go into a convolution layer you've already seen. Each neuron. So when we talk about layers, they all, at least in neural networks, they all will have neurons, which pretty much do this, right? Neurons will take will have a bunch of weights, will have a bunch of inputs. They'll multiply the weights with inputs, sum them up, and do a nonlinearity, like a max of 0, sum, or 1 by 1 plus e to the power minus sum. Okay? That's what they all do. So even convolution layer will compose of neurons, which do the same thing. The max of 0, sum, or one of these. Okay. But collectively, the output that they give, at the neuron level, it's not easy to understand, but collectively all these neurons will output something which is going to be a 3-dimensional array. Okay, so that's the interesting part. So individually they all act as the same way as what a feedforward neural network's neuron does, but collectively this bunch of neurons output a 3-dimensional array. Okay, I mean, this is all for understanding. It's not like I can always reconfigure them and say it's not a 3-dimensional array, it's a vector, but conceptually this is how it will make sense. In terms of, remember our original goal for CNN, we are all trying to, because we have images, we don't want a fully connected network because we'll have lots and lots of weights. I want to reduce the number of weights. Okay, I want to exploit the image properties, something or the other, to get to lesser number of parameters and still have a neural network. So the neurons will remain the same, but the way the neurons look like in a layer is going to be such that I'll have lesser parameters, and I'll be passing on 3-dimensional arrays rather than vectors across layers. So as I said, the convolution layer does what a regular neuron in a neural network, in a feedforward neural network does. What the pooling layer does is, as I said, it performs downsampling, okay, in the spatial dimension. So what is meant by downsampling? I just mention this here. So let's say I have numbers 10, 11, 12, 8, 5, 7, 8, 3. Let's say this is my matrix. Pooling can be just thought of as, okay, I'll pick a small submatrix in my matrix and pick one number out. Downsample. So let's say I pick the maximum number out, so I'll pick 10. And let's say in the next batch, 11. And in the next batch I'll pick 12. So I just reduce the dimension, which was 2 cross 4 here, to 1 cross 2. That's what pooling does. Okay. So if the input was 32 cross 32 cross 12, it only works on 2 of the dimensions of the 3D array. So it's gonna, let's say, divide by 2, then it's gonna output 16 cross 16 cross 12. So the last coordinate is special. So it doesn't pool anything on the last coordinate, but it pools on every slice. So a 3-dimensional array is just a slice of a sequence of matrices, right? So it's gonna kind of downsample on each slice, but keep the number of slices the same. Okay, and fully connected layer is input can be any tensor, but the output will be this 1 times 1 times 10, and it will be just like the fully connected feed-forward neural network. Okay, so let's say the input is 16 times 16 times 12 because that was the output of my pooling layer. The output of the fully connected network will be 1 cross 1 cross 10. Okay. So I just want to end at this diagram, and in the sense there are a couple of slides more, but in terms of the CNN we're going to carry forward to the next lecture. But so what exactly is happening, I'm going to repeat this, is that we went from a pixel which is from pixels which are 32 times RGB images to scores which are 10 in number, and these were the layers: input, con, pool and FC. Some layers have parameters. As I said, the neuron in a convolutional layer is just going to be the same neuron that we saw in the feedforward neural network. So it will have parameters, the weights and the bias. Okay, fully connected anyway, it's the same neuron as what we saw in the feedforward neural network. So it will also have parameters, the W and bias, the weights and the bias. The pool operation is like a non-parametric operation. You know, it says pick 4 numbers, pick the max of 4 numbers, right? The parameter is 4, but you don't really care about, you don't explicitly consider it as a parameter like the weight parameter. Okay, and still the operation, the meta algorithm, as in the classification pipeline, is still the same. We want to optimize these parameters of the parameters of the convolution, neurons in the convolutional layer, neurons in the fully connected layer, such that we achieve scores consistent with the image labels. So in CIFAR 10 there were 10 image labels, right? We saw the 10 image labels. So we still need to do that SGD with backprop such that we converge to the right parameters for the con and the fully connected layers, such that the model is going to classify really well on a held out validation or test set or something like that. Okay, so we're going to continue again about convolution in the next class, but you can actually see a great demonstration by so you have these slides, so you can probably look at it offline. So there is a so somebody implemented CNN in the browser. Of course it's a smaller CNN, but you can actually see how it does on the CIFAR 10 dataset. So to get an idea of how does the input look like, how does the output look like, and what the accuracy is. You don't care about the internals of the layers because we're going to discuss it next time. Okay. A couple of quick things. There were a lot of choices we saw in the first 2 lectures, right? There was model choice. There's nonlinearity. There's number of layers, number of neurons. You need to pre-process the data, right? You also need to initialize the parameter. What is W0, B0, from which you need to kind of do your gradient descent. You also need to choose the learning rate, that step size or the alpha that you saw in the gradient descent update. You also need to monitor learning, right? How do you know you're learning, right? There was an L number that I assigned to W0, B0. There was another L number that I assigned to W1, B1. This L, the second L hopefully is lower, so you can plot it. It's a scalar, and see that the L is going down, right? It's a loss, so you should go down. So you should improve. So you need to monitor that learning process. How are you going to do that? And you also need to do something called cross-validation for the hyperparameter. You saw that lambda thing, which was balancing the regularization and the loss. So those are all the practical considerations which I have not put in the example scripts, but we will see how they also kind of affect heavily how the models are chosen at the end of the day. So for example, the linear model that I showed, which was really bad, decision boundaries were overlapping across classes. Maybe by cross validation, maybe by some other things, I can improve the accuracy of the linear classifier. One final thing is, in spite of all these design choices, for 90% of the applications, you want to pick an architecture that works well on an established data set, like the ImageNet, right? We know on ImageNet that the classification task is totally solved. The classifier, an artificial, is an algorithm with a bunch of weights, can do better than humans. So even if you make a human sit and actually classify your input, he will do worse than classifier. So you want to pick the same architecture as them and maybe specialize to your application. For example, the online retail store owner who wants to classify clothes, for example. Maybe there are several clothes categories in ImageNet itself. Then you may want to kind of specialize specialize the weights a little bit more towards your application. So we will see all this later. What I'm saying is that even though there are lots of design choices, they are just for knowing that all these such architectures are possible. But empirically, there have been some architectures which are successful. Just focusing on that would be good unless you're working in deep learning research. Okay, and and you can go through these slides to get a better idea of CNNs for the next lecture. That's it. Yes.
Not from BBA. What is this?
MSBA.
MSBA. I'm a PhD student in electrical engineering.
You see.
So basically, I do research in UI. I tried to understand what would be nice for me from practice. So
Okay.
I did get a petition for enrolling into the course, but I don't want to burden myself with the course. I want to do the project. So I
Yes,
have
yes.
a friend and she was willing to be my group mate. So
Yes, yes.
would it be fine for you if me not being the enrolled student to work on the project with her?
Okay, she is taking for credit.
Yeah, she's an MSP.
Okay. Okay.
Well, I
Have you
want-
spoken to Sid by any chance?
I asked him, so he gave me the petition to enroll the course. Then enroll into the course yet because I don't know. You have exams and stuff too.
One exam, but that's in class, so it should be fine. It's an in-class exam, which is going to be not difficult.
So, and what are the projects?
No, project is quite open-ended, but I'll just set some guidelines so that we don't steer off into some uncharted territory. In terms of
So basically,
projects are just going to be applications of deep learning to your domains. That's it.
And,
I mean, you can do more. But
yeah, that's fine. And, so deep learning is fine. What else are you going to teach? Graphical
I'm gonna
models,
teach graphical
HTML?
models. Yes, I mean not complete details, but something which is worthwhile, and also reinforcement learning and online learning.
So okay, I just wanted to ask you that me not
It should-
enrolled in the course. Is it
I don't know. I can just double check. So this is my first time teaching
I
the course, so I just have to double check with it. If he's fine, then I should be fine.
Okay, so
He hasn't.
remind you.
Just drop me an email. Do you have my email address? Okay.
I'll send you notes.
Yeah. Drop me an email without fail. Okay.
So I had a simple question. Like, towards the end of the course, will I be able to build something like, I put the link of an image and then it creates tags for it and it gives me a confidence level.
Yes. You can do. Yes.
Like
that
we
is-
learn all of it in the course and by the end I
Yes.
can do that myself.
Yeah, I mean, as long as you're not too ambitious, like the tags, there has to be training data with tags and so on. Then you can do it with general image, which is like pick an image from
Yeah, but
the
like a
internet
small scale level
some
of
domain.
that I can do.
Yeah. But you should be familiar with setting up a web service and all that, because this is only going to focus on training a deep network for achieving that. But if you want to do it you want to set up a web service like Flask or something on Python. I don't know how much you know about web servers, HTML. You need to set up all that to actually have a demo, right?
Yeah.
But otherwise,
But the backend I can do. Like maybe someone else can do the demo.
Yes.
The front end thing.
Yeah. The hope is that we can do that. I mean, let's see how well we pace ourselves.
Okay, because it's like one of my friend is working on a startup in Hyderabad around deep learning, and they are doing this thing.
Yeah.
And then they are selling that to the government for toll tax, like you.
Yes. Yeah.
So I was like, if that is such a big deal, like, they can make money out of it. How can
Yes.
it be so simple? Like like one.
No, it's not simple, right? You're a master's level student, right? Yeah, you can kind of focus on niche and really go in depth, right? You can see where the ROIs is going to be worthwhile at the end of the whatever the business goal is, and deep learning solution. There's a lot of low hanging fruits that you can touch. Yeah. Yeah.
So when you introduced convolutional neural networks,
Yeah.
you said that it is going to be computationally less expensive than
There are less parameters. Yeah, it's going to be less expensive because there are less parameters.
Yeah, I'm not really getting the intuition of that as of now.
Less parameters. So if you have less parameters, let's say all the parameters are getting multiplied.
Yeah,
I have less multiplication.
I'm not getting the intuition of less parameters.
I
Because
will. That's we have not yet got into why there will be less parameters. So you can look up the slides to see the answers, but we have to kind of skip a lot of things because we spent a lot of time revisiting the first lecture. Next time we will not do that. We'll directly pick up CNNs and see how we can reduce the parameters. It's all about spatial invariance, right? Like let's say you want to detect an edge, whether the edge is there at the top of the image or the bottom of the image, you don't need too many parameters to figure that out. Figure an edge out. You can basically kind of apply the same weights at multiple locations. That's the intuition, but we'll get to that next.
actually, how is it very different from feature engineering? Because from what I understood, it's like
No, because it need not be an edge detector. It can be anything, right? I didn't tell it to be an edge detector, but it can become an edge detector if the classification accuracy is high. If it becomes an edge detector, whatever the parameters of an edge detector are, it's going to be just numbers in matrices, small matrices. Whether they become an edge detector or some other detector, that's completely data driven. I am not specifying that it has to be an edge detector.
okay.
That's why it's less feature.
So what I'm understanding from this is that you're not exactly specifying any features, but based on the data, the convolutional neural network will find out that these features are important. And
Yes.
does it
Yeah,
also.
edges may not be important for some other classifications.
Yeah.
Right?
So they might have something like symmetry or whatever.
Yeah,
So-
those types of things. Yes.
Those are the things we are. Okay. Thank you.
Yeah.
The number of non-linearities that we have.
Yeah.
So, is it obvious that if we take the ones which have come more later in time, they would give us better results?
No.
Not necessary. It would depend
I
upon
think
the
the
type
default is ReLU
of. Okay. Even
because that's the one which is showing a lot of promise. But the subsequent ones are trying to push better than ReLU, right?
okay.
Maybe in their papers it does better,
And
but it's not a practitioner. I think if you're a practitioner, you should get a whole pipeline running with ReLU and then maybe experiment with other things because it's just a simple function called change, right? You just use the same function, just redefine the function and see whether it performs. But
in terms of implementation, there is no complexity involved. We have we just change the activation function. That we
yes.
Okay. And this pooling thing that you mentioned,
Yeah.
does it work because pixels adjacent to each other are quite similar?
Yes.
That is one of the reasons.
Yeah.
Okay.
And the other reason is computational in nature, nothing to do with intuition.
Mhm.
It's just that if you retain the same size, it just because let's say the original image had 3 color channels. What happens is convolution layers kind of add more in depth. So if it was originally 3, there could be 100 in terms of depth. I'm telling like 3D matrices, right? 3D arrays. If you don't reduce the height and width, then you are in trouble because then you have bigger and bigger 3D arrays. So because we are increasing in depth, we want to reduce in width and height. And the simplest way to do it is to shrink the matrix by just doing, similar as you said, like take the average or take the max of neighborhood quantities values.
And which Python do you use? 3.5 or 2.
I'm using 2, but that's because I had installed a long time ago.
Okay, because if we'll run that same code on 3.5, it's not
You need
compatible.
to,
We have
yes,
to make some
yes.
changes.
Yeah,
So that's right.
maybe you
And-
can, you
But,
can get bonus points by putting a link on your discussion board that this is the Python 3 version for the code shared in the
Okay,
lecture.
that is
Yeah,
okay. And
yeah. Then I will
because,
remember your name.
Because for this one installing TensorFlow on Windows, we
Yes,
needed
yes.
3.5.
Yes, I know.
So that was the reason I installed 3.5.
Yes. Makes sense. So if you can convert, if it's too much of a painstaking thing, then I will try to do
I'll
something.
check.
Uh,
If it is, otherwise I'll do it.
Actually, if you have used Anaconda, then you can do
Yeah.
Conda virtual right? Not virtual environment. I think it's called.
Jupyter.
No, you can create a virtual environment. Have you used virtual environments before?
So I'm using Jupyter to.
Yeah, Jupyter.
Yeah.
But what happens is you can run simultaneously multiple versions of Python.
Okay.
So although I have Python 2, I can also run an instance of
Yeah.
Python 3.5 and also start a IPython related to that
Okay.
on the same machine.
Okay.
There is no version
In
conflict.
parallel, you can have.
Yeah.
Two different.
Yeah, there's some. These are called Python virtual environments, not the virtual box and all
Okay.
that.
I want to try that.
That's a very useful thing because you don't want to pollute your rest of the system, OS infrastructure by
Right.
installing Python into /user/whatever. I mean, depends on where you are, which OS you have. So, but if you can convert them and post the links, then it will be good.
Sure, I'll try.
Yeah. Thank you.
Thank you.